Well, hi everyone. Thanks again. My name is Zach Hoylman, and I again am the Assistant State Climatologist in the Montana Climate Office and a Research Assistant Professor at the University of Montana. I'm excited to present some of our recent work entitled Drought Assessment Has Been Outpaced by Climate Change, Empirical Arguments for a Paradigm Shift. Firstly, I'd like to thank NIDIS for facilitating this gathering and providing a space for this conversation. Before I begin the presentation, I wanted to take a moment to describe what this research is and what this research is not. This research seeks to understand the impact of climate change on traditional drought assessment methods and quantify the impact of a changing climatic baseline on those assessments. In essence, this work represents an optimization problem that seeks to balance the statistical needs of drought models with the intention of accurately describing current day contemporary drought risk in the light of rapid climate change. While this work questions conventional practices in drought monitoring, and particularly the reference periods used to calculate drought indices like SPI and SPEI, we in no way seek to undermine the important work of drought monitoring in the United States. We strongly support the need for national drought assessments and appreciate the enormously large task that USDM and its partners take on every week. For that, we would like to say thank you. And as many of you know, the Montana Climate Office is an active participating member in national drought conversations and assessments, and I absolutely appreciate how hard the task of drought monitoring is, and I'm only responsible for one state every 5th week. So again, I want to acknowledge the monumental task in front of the USDM and its contributing partners. This research provides an assessment of the impact of climate change or non-stationarity on our perception of aridity as reflected in drought indices. Our goal is to promote an objective, realistic, and standardized workflow for the entire drought community. We believe that consistency is a key component of objectivity. And finally, I want to say that this work was derived via many conversations with state and federal managers, scientists, and practitioners that are all interested in accounting for climate change in modern drought assessments. All right. So I want to start this talk by thinking about drought in the United States generally and reflect on its impact to the communities and people of this nation. Of course, I really don't need to say this to all of you, but I did want to start with a little bit of context. So drought has significant effects on the agricultural and ranching communities across the country. In fact, it's been estimated that major drought events since 1980 have cost an average of $9.3 billion per damages an event. National risk mitigation efforts are in place to help communities impacted by drought. Some of these efforts include livestock and agricultural insurance or relief programs that help producers persist through extreme events. Financial assistance associated with these disaster relief programs are essential to sustain our national agri-system through periods of abnormal dryness. And drought monitoring is used to trigger these economic relief programs in some cases and is supported by a large community of scientists and water resource managers across local, state, and federal entities. So how do we monitor drought? As you all know, one popular method is by using a variety of drought metrics. Drought metrics use historical conditions to contextualize how current conditions compare to some reference period. Drought is, by definition, an abnormality in dryness. And in order to determine abnormalities or anomalies, drought scientists use reference periods to define the expected distribution of outcomes given some historical observed variability. In general, conventional methods in drought science prefer long periods of record or longer periods of record to define the reference period. This convention is generally supported by suggesting longer periods of record incorporate a wider range of extreme events and therefore better describe the true distribution, especially at the tails. However, the question arises, what if the distribution is changing in time? In other words, what if the underlying process is non-stationary? For example, if your reference conditions are fixed and aridity becomes the new normal, is that location in drought or experiencing average conditions? This is a key question that requires conversation amongst the drought community. This consideration highlights a few major research questions in drought monitoring and leads me to the first of our major research questions. First, how much data is needed to accurately compute drought metrics? This question tests conventional methods in drought monitoring to understand the statistical requirements for parameterizing drought models. And second, do longer climatology lengths produce bias in contemporary drought assessment? So to better understand our how non-stationarity may impact drought assessment, I would like to describe our conceptual model in a little bit more detail. Let's consider a theoretical precipitation distribution that's changing in time. This figure shows accumulated precipitation over some arbitrary timescale on the horizontal axis. On the vertical axis, we show the associated probability density function. The different colored lines represent different time periods, starting with a 30-year time period at the beginning of the 19th century in blue to the current 30-year distribution shown in red. In this theoretical location, precipitation dynamics are getting drier and more variable over time. Here we can see that the driest conditions early in the century, shown on the left side of the blue distribution, are closer to the average conditions from mid-century, shown in green, and are actually relatively wet when compared to the current 30-year distribution. This idea has serious implications for computing drought metrics. For example, if we use conventional methods for computing the expected distribution, we would prefer to use the longest reference period possible. This is represented using the black line on the right panel. In this case, the driest expected conditions for the temporally integrated distribution are actually only slightly dry when compared to the conditions expected based on the most recent 30 years. If we were to observe an event such as this, the severity of the event would be considered more severe than is relevant based on contemporary conditions. So do we see evidence of this temporal shift? Here's data from a Global Historical Climate Network, or GHCN site in South Carolina. What I'm showing here are the parameters used to describe precipitation distributions when assuming a gamma distribution. On the horizontal axis is time, and on the vertical axis is the parameter value. I computed these values using a 30-year moving window that shifts each year. What you can see is that there's a nonlinear and directional shift and change in these parameters over time. This is associated with changes in the precipitation central tendency and variance over time. In general, this site has been getting drier and more variable over time, similar to our conceptual model. To better visualize this, we can plot the associated probability density functions color scaled by time. The black and white dashed line represents the temporally integrated distribution that would be calculated using the entire period of record. This analysis shows that precipitation dynamics at this particular site are non-stationary. Specifically, you can see a progressive shift from right to left over time. And this idea is not particularly new. We know that precipitation dynamics are changing through time, and this has influences on water resource management decisions. But there's still a need to intentionally incorporate this concept into modern drought monitoring. Okay, so if we assume that climate is non-stationary, it is important to understand how much data is required to accurately parameterize drought models. This brings us back to question 1. To address this question, we will use Monte Carlo simulation methods to estimate drought metric error. To do so, we will begin with a known stationary distribution. Using this known distribution, we can quantify the relative change in error associated with differing climatology lengths to define the reference period. Here, we will also compute the absolute error in the associated standardized precipitation index, or SPI value. SPI is, of course, one of the most common drought metric indices used to estimate meteorological drought and describes precipitation anomalies. However, it's important to note that while we are focusing on SPI in this particular analysis, the concepts that we are presenting here today are relevant to any metric that uses historical conditions to estimate anomalies. For example, things like temperature percentiles or the SPEI, etc. Then we will modify this method to use observed estimates of climate from GHCN sites to emulate non-stationary conditions. So let's start with a precipitation distribution that's well described using a rate parameter of 0.3 and a shape parameter of 2.5. To obtain these results, we generate random data from this known distribution and randomly sample that data using differing climatology lengths. We then estimate the parameter values associated based on those random samples using L moments. The horizontal axis shows the number of observations in the climatology, and the vertical axis shows the estimated rate and shape parameter value. The black line represents the median estimate over 1,000 iterations, and the gray ribbon represents the interquartile range of these estimates. As you can see, the range of estimates shown as the gray ribbon width is very large with a very limited sample, say 3 observations. This uncertainty declines significantly when 15 observations are included, and from there, there's a modest reduction in uncertainty from 15 to 30 observations. Beyond 30 observations, there is a relatively small reduction in that uncertainty. And just for reference, here's what that distribution looks like as a histogram. As you can see, it's a reasonable approximation of a theoretical precipitation distribution. And if we extend this analysis to estimate the associated cumulative distribution function and SPI absolute error, we can see a decline in uncertainty and error. Now remember here, we know what the actual distribution is because we define the distribution, so we can actually calculate the true SPI and CDF error. SPI error declined sharply from 2 to 15 observations. Error decline then slows substantially to achieve an average error of 0.16 SPI units when 30 samples are included. Again, only minor reductions in error are then associated with sample sizes extending to 60 or 90 observations. In summary, error is relatively low with sample sizes as low as 30 observations, beyond which only minor error improvements are made. So, but is this error curve parameter specific? For example, maybe I just chose a distribution that was coincidentally easy to calibrate. Here we extended the analysis to include a random sample of parameter estimates using observed parameter space derived from roughly 5 million SPI calculations. As you can see, a similar error curve is observed regardless of the gamma distribution used, confirming that this error analysis is generally applicable to common SPI calculations performed across the United States. This brings me to an important question. What is the relevant reference period for drought? It is important to remember that drought is, by definition, a relative phenomenon, both in space and, very importantly, in time. When we consider that real-time management decisions are being made on operational drought monitoring, it is clear that monitoring is designed to assess and mitigate current-day drought risks. Without a dynamic reference frame, some places may transition to a state that is considered to be in drought on average with respect to the last century. Alternatively, if a shifting reference frame is adopted, anomalies will reflect current climatic variability and current day expected distributions and conditions. Besides, shifting reference frames are quite common in climate science, as we all know. 30-year normals have been adopted to at least partially account for non-stationarity and have been formally used since the 1930s. And this is critical to describe realistic expectations in the light of climatic variability. As an example of this practice, here are temperature normals computed for the continental United States compared to the last century. As you can see, temperatures have been warming gradually across the country for the last century. In this case, if the reference frame did not shift, one would conclude that most, if not all, annual conditions were anomalously warm in the most recent period. While this is true from the perspective of the century scale reference frame, it is not necessarily accurate from the perspective of the last 30 years. This practice of updating normals is used specifically to better approximate what temperatures are likely to occur today. So has the United States transitioned to a new normal of drought? Well, a recent paper in PNAS looked at this specifically and evaluated how a continually changing baseline impacts our understanding of major drought events. The authors conclude that portions of the Western United States have already transitioned to a new climatic state where mega drought conditions are now the average climatic state. More specifically, their analysis suggests that this transition occurred in the early 2000s. This work concludes that if stationary assumptions are held, locations like the Western United States could remain in this state of mega drought for the remainder of the 21st century. So if a 30-year moving window convention is applied with the understanding that 30 years of data meets our statistical requirements and that we have already transitioned to a new definition of normal in some locations, we can now begin to estimate how error changes across differing sample sizes in a non-stationary environment. Here, we're using a similar Monte Carlo simulation, although instead of using a single distribution to generate data, we're using many distributions observed empirically from our South Carolina GHCN site. In this case, we're estimating the error for the most current year's value, 2020, by estimating the distribution using progressively outdated information as the climatology length increases. So we're going to be sampling from the red distribution early on and moving across more and more towards that blue distribution as we go further and further into the climatology length. Here we can see that error initially declines, similar to our non-stationary example, but then subsequently increases after roughly 30 years. This increase in error is associated with the estimated distribution becoming increasingly outdated as older observations are included. In other words, the conditions from the early 1900s are no longer good representations of today's variability. so error increases. In summary, error can actually increase with greater climatology lengths if the contemporary climate is significantly different than the distribution at the beginning of the period of record, and the intention is to accurately describe current day drought severity. If we emulate this analysis across many sites and drought timescales, we can see that the error trajectory for any given location is site and timescale specific, and importantly, error does not necessarily decline given more observations. So given this analysis, a fundamental concept is highlighted. Drought monitoring must balance two distinct needs. Firstly, there are fundamental statistical necessities where a certain amount of data is needed to estimate any distribution, stationary or otherwise. Drought monitoring and climatology analyses have conventionally used only data from the past in defining these distributions. So that's what we're assuming we're going to do here. However, in a non-stationary environment, using too long of a reference frame into the past may skew your expected distribution outside of realistic outcomes, increasing error and potentially biasing our assessment of drought severity. In many ways, this also presents an opportunity. By using shorter reference frames that update periodically, drought assessment will provide more realistic descriptions of how likely any specific drought event will be today. This may incentivize adaptation in aridifying communities because the same level of dryness may reflect less of a climatic anomaly in a location where climate is getting progressively more arid over time. Which brings us to the second of our major questions. Do climatology lengths, long climatology lengths bias our drought assessment? To investigate this question, we will compute drought metric bias for two different reference periods. The longest or period of record climatology versus the most recent contemporary 30-year climatology. This will allow us to empirically estimate the bias associated with using a period of record climatology. This analysis was conducted using almost 2,000 GHCN sites across the continental United States with at least 70 years of complete spring and summertime rainfall data. We compute SPI for every day for every site between June 1st and August 31st, 1991 to 2020. This analysis incorporates roughly 5 million probability distribution estimations. Here are the results using a 30-day timescale for the SPI calculation. In this map, we're looking at the daily average summertime bias in SPI from 1991 to 2020 during exceptional drought conditions. As you can see, a large portion of the map is red, which shows that the period of record SPI values are biased dry when compared to the contemporary 30-year distribution. In other words, the severity of drought conditions are exaggerated when using the longest period of record. In general, large portions of the west, southwest, and southeast are affected by this dry bias. Alternatively, locations with blue colors represent locations where the period of record is biased wet or drought severity is underestimated. These patterns are generally consistent when 60 and 90-day timescales are evaluated. These maps demonstrate spatial patterns of drought bias due to climate non-stationarity and highlight the need to reconcile this important consideration. We argue that leveraging 30-year reference frames into drought monitoring balances statistical necessities with the need to accurately describe current day risk profiles for drought assessment. So the implications of this research are primarily focused around aligning drought monitoring with contemporary drought risk. If drought intensity is assessed using stationary assumptions, drought severity will be exaggerated in locations that are experiencing aridification. In other words, there will be a dry bias with respect to actual contemporary conditions. Further, under this assumption, it is likely that certain places will be in drought on average as climate continues to change. Alternatively, drought conditions will be underestimated in locations that are trending wetter. Importantly, this concept applies to any metric that uses a stationary reference frame to standardize values. In fact, this concept may be even more influential for metrics that utilize temperature and evaporative demand in the context of climate change. By adjusting drought methods to be based on a moving window, drought assessment will better reflect current day drought risk to affected communities, be more standardized and consistent across data sets with differing periods of record, and account for climate change in the future. And here I really want to emphasize that methods right now are broadly inconsistent, especially when comparing across data sets or when calculations are conducted with station data with varying periods of record. For example, if we compare the difference in USDM classes associated with a 1-month SPI map using a period of record data set from PRISM, which of course starts in 1895, compared to that of a recent 30-year reference period, we can appreciate a real-world example of this research. Here you can see that there's a 1 or 2 drought class difference between these data sets in the Southwest and across parts of Wyoming and Nebraska. Here, to conclude, I've compiled a list of some commonly used data providers to highlight the inconsistency of reference periods across data providers. We believe this inconsistency not only limits the objectivity of drought assessments, but can also be confusing or hidden from users. Ultimately, further dialogue is needed within the drought and water resource community on how to better characterize drought and contemporary risk in an era of rapid change. I'm hoping that today can be a significant step in that conversation. And with that, I would like to say thank you. This work has been published in the publication that you can see here. And to begin the kind of open discussion portion of this meeting, I was just hoping we could start with potentially any methodological questions that anyone had. And then from there, we can move on to general discussion about whatever we might want to discuss. Thank you.